Hi. Since coronavirus is such a hot topic these days, and lots of us are taking tests, whether it's if we want to go to some sort of event or go travel, or just for work, or whatever it may be, we want to know if, when we test, are we actually testing if we have the disease, or are we just falling victim to an inaccurate or unreliable test, right? So we want to look at sensitivity and specificity. Right, so if we go to test and get a positive result, well, that doesn't necessarily mean that we actually have the virus. We could test positive and it could be a false positive, or we don't actually have the disease. So if we're actually negative and we test positive, then, well, you can forget about your vacation, unless maybe you have time to take another test, and that one comes back negative, and then probably even in that case, you might have to take a third test to show that the first one was actually false positive rather than the second one being a false negative. And so this one is more of a hassle, and it would complicate work environment or your ability to attend some function or travel. It's not necessarily dangerous. The actual dangerous one here is when people test negative and they're actually disease positive, so it's called false negative, right? In this case, the person might think they don't have the disease when they actually do, and so they might spread it around if it's communicable. In the case of COVID, it is. And more importantly, they might not seek medical treatment. In the case of COVID, chances are you're going to get better. There's a 97%, 98% recovery rate and more across the world, depending on the age group and other underlying conditions. However, if for another disease like cancer or something like that, depending on the cancer, if you get an early false negative, you might think you don't have it, and then you would avoid early treatment. In any case, whatever the disease, if you avoid treatment, you might have worse outcomes. There's a pretty decent chance that you're not going to fare as well with the outcomes. And so when we add up the true positives and the false negatives, we get the entire disease population, right? When we add up the false positives and the true negatives, then we get the population without the disease. When we add up all the negative tests, that's including both false negatives and true negatives, people who are actually negative. And when we add up all the positive tests, that's including both the true positives and the false positives. And so what we got again is sensitivity, which is a ratio of the true positives to the total number of diseased people in the population. Right? We can express that as a percent by multiplying it by 100. And this will tell us basically, does the test tell us the truth? Is a person likely to be, or almost always, positive? Do they actually have the disease given that they test positive? So we want the percent or the ratio of true positives to all of those in the disease population. We want the false negatives to be as slim as possible. And ideally, we want the false positives to be as slim as possible. But that's not quite as important for health outcomes, certainly for convenience and sanity's sake. All right, specificity relates to those. So we're taking the true negatives, those who are actually negative, don't have the disease, and we're distinguishing them as a ratio of the entire negative disease population, right? So true negatives divided by disease negative, that's our specificity, right? And then we've got a couple other ratios that we'll work with in just a moment. So I found on the British medical website there were 5 different tests, but let's look at these 3 different tests. And they come in different varieties, they use different techniques, and they take a different amount of time, right? So this one takes 24 hours, this one takes 90 minutes, this one takes 30 minutes. And, well, you might reliably or accurately guess that the one that takes more time would be more reliable. However, if we compare the sensitivity, again, that's the likelihood, or roughly the likelihood, we can think of it that way, the ratio of true positives to disease positives, we can see that this one is a 90-minute test. The Lamport actually performs the best. And then, somewhat predictably, the one that is the shortest, that's the most instant or rapid form, has the lowest ratio, the lowest rate of catching those that are actually positive. Right, so we've got some different statistics. We can multiply by 100 to come up with percent, 0.88, just 88%. So 88% of the people who test positive actually have the disease in this case. And about 99% of people who test negative actually don't have the disease, which is good. We always want to be accurate and reliable, right? So what I've got here is another one of these charts, right? And we want to put in some numbers. Say for our base case, we're just going to say, well, we know that sensitivity is 88. So we know that the true positives are 88, and that means the disease population is 100. And then we just subtract 88 from 100, we get 12, right? Just a base case. We can fill in this chart, given sensitivity and specificity. And then if we know that the specificity is 99, we're going to put that here. That means the true negatives are 99, or 99% of 100. And so, give it a base case, we've got a total population of 200. And if our total population is 200, that means that if we look at this one and this one, they're the same. That means disease positive and disease negative have the same population, or they are the same amount in the population, the larger population, which means that the PV, the prevalence of disease, the disease positive divided by the total population, that's 50%. 200, 100 over 200, or 100 in 200 is 50%, 1.5. Right? And if we want to add these up, 88 and 1 is 89, 99 and 12 is 111. So now we can calculate the PPV and the NPV. The PPV, as seen here, is the positive predictive value. So you go into the doctor's office and you take a test. And given the type of test, that doctor wants to know, well, what is the likelihood, what is the value of that test, what's the predictive value of the test? So he wants to know the likelihood that if you test positive, that you are actually positive. And so we can calculate that by taking the true positives over the test positives, which is 88 over 89. 88 over 89 is equal to 0.989. And so there's a 99% chance if you go into the doctor's office and you test positive, then that doctor is almost certain that you have that disease and he'll prescribe some course of treatment. The negative predictive value, NPV, is the true negatives divided by the test negatives. True negatives here are, let's see, test negative, true negative, that's 99. And the test negatives is the sum there, 111. And so the NPV in this case, 99 divided by 111 is 89.2% or 0.892. And so it's slightly lower. You can see that if you test negative, the doctor is slightly less sure that you're actually negative. But given the relative certainty there, he might say, well, just keep an eye on it, and if anything changes, then get back to it. Probably not going to prescribe anything given that you tested negative. There's a fairly decent chance that you are actually negative. Let's take a look at the second one. You go into the doctor's office or you stop by the local testing station. 90 minutes later, you get yourself your test results, and it looks like it's pretty darn accurate. 98.7%, 99.7% sensitivity and specificity. So let's fill in our chart. But in this case, let's move away from the base case. We know that the prevalence of disease is 10%. And it's 10% of 300 million in the total population. And so I'm just going to take a ratio, 10% of 300 million. I know that 30 million are diseased because that's our PD, right? We're going to have 300 million total over here. And that means that 10% of 300 million is 30 million. And so I can take this number and subtract from that this number here, and I'm going to get the negative population, which is 90%, or 270 million. Well, that was simple. And I would know this by compiling statistics from local health departments and things like that. All right? So now we know the sensitivity, specificity, and we know the total population number. Let's work through some of these. And so if I know that the sensitivity is the true positives divided by the disease positives, I know my disease positives are 30. And so what I want to know is 98.7% of 30. and I find out that it's 29.61. And it's 29.61 million, just move the decimal point over. Right, so that's our true positives, they test positive, they are positive. So it's 29.61 million of those disease positive people have tested positive. And then the remainder is going to be those who have a false negative. Remember, those are the dangerous kinds. And so I'm going to take 30 minus 29.61 and I get 0.39. And then I want to know the specificity. This relates to the true negatives over the disease negatives. I know the disease negatives are 90% of the population. And so that's 270 million. So I want to know 99.7% of 270 million, which is 269.19 million. 269.19 million people tested negative, and they were negative, that's the true negatives. And then the remainder of those who are actually negative have false positives, and those are the inconvenient kind. Those are the kind that might also put people onto a course of action or course of treatment, which could in fact be dangerous. If a doctor starts prescribing medicines based on that first test without a second opinion or a second test, well then in fact there could be very adverse reactions to such medicines that are not necessary. Right, so if we have 99.7% true positives, then the remainder of 270 minus 269.19 are the false positives, and that is 0.81 million. Right, so now let's look at the PPV and the NPV. The predictive value, the positive predictive value, is the true positives divided by those who tested positive. Let's sum up these first of all. We get 30.42 million people tested positive, and we get 269.58 million people tested negative. Right, so to find our positive predictive value, we got the true positives divided by the tested positives. That means 29.61 divided by 30.52, which is 0.973, or 97.3% chance that if you tested positive, you are positive. Next, negative predictive value is those who are truly negative divided by those who tested negative. So we got 269.19 million divided by 269.58, and that equals 0.999. So it's slightly more accurate or reliable when it gets a negative. And that makes good intuitive sense here, given our sensitivity and specificity. Third one, the direct RT lamp takes 30 minutes. It has a sensitivity rating of 0.67. In this case, let's take a look at a population of roughly 67 million, and about 6% of the people are infected. We know that from population statistics from local health departments or the National Health Service. And so, if we have 67 million here, that's our total population, and we know that 6% of that 67 million are infected, 4.02, so we get numbers coming in, and then we can make predictive models based on rolling averages and things. We know that any given day during this period of outbreak, about 6% are or have been infected. And so then 67 minus 4.02 is the remainder who are not infected, that's 62.98. That is the population that is not diseased, right? Okay, so now let's look at our specificity and sensitivity. Sensitivity is 0.67. 0.67, then go back there, sensitivity 0.67 equals the true positives divided by the disease positives. Disease positives is 4.02 million. And so 0.67 equals true positives, that upper left corner there, divided by 4.02. And we end up getting 2.69, which is 67% of 4.02. And so the remainder, 4.02 minus 2.69, is 1.33, or 33, roughly 33% of 4.02 million are positive, but they tested negative. That's not good. So we're not going to recommend this test, just based on the sensitivity. It's way too low. Let's look at specificity. This is also the lowest specificity, though you can see that specificity is much it's higher generally, given a comparison between sensitivity and specificity. That means it's easier for these tests to tell you if you're negative than it is to tell you if you're positive. There are a lot of chemicals and reactions and things going on in the body, and so when it's looking for a particular reaction to make the test turn positive, that is more difficult to find than it is to have an absence of that, whatever it is that makes the test positive. So specificity, once again, 97% of 62.98 gives us 61.09 million people are negative and they tested negative. The remainder, 62.98 minus 61.09, are false positives, and that is a bummer for those 1.89 million people still. So 97% looks good on paper, eh? But not really in practice, because you still got 1.89 million people, which is a lot of people who just tested positive and they aren't, so they might start a course of treatment even though they don't need it. Right, so let's add those up. 2.69 and 1.89 equal 4.58. 1.33 and 61.09 equals 62.42 million. And looking at our PPV, our positive predictive value, what percent likelihood or confidence does the doctor have that if you tested positive, you are actually positive? We're going to take that 2.69 divided by 4.58. So the ratio of those who are true positives to those who tested positive, 2.69 divided by 4.58 gives us a PPV of 0.587, which is even lower than specificity, and you might see a trend here. When sensitivity is higher than, well, I suppose it depends. It also depends on prevalence. So the prevalence is related to the prevalence population. Sensitivity and specificity are all interrelated, leading to our PPV, our NPV. So a higher sensitivity, in this case, does not necessarily mean a higher PPV, because when you have a higher prevalence, then PPV is affected such that lower sensitivity is actually driving that number up higher. All right, and finally, NPV, negative predictive value. True negatives divided by tested negatives. We've got true negatives at 61.09 million, tested negatives 62.42 million. That gives us an NPV of 0.979. There's a 97% chance in your doctor's office that if you test negative, he or she will recommend a course of treatment for nothing. Right, so a lot going on here. Maybe in another video we can look at what your actual likelihood of death is given if you test positive and then seek treatment, or if you test negative and then don't seek treatment, etc. Okay? So be aware of these statistics, and let's not be rash while we're dealing with our new medical scientific environment. When we walk outside, let's try to maintain calm, keep calm and carry on, and let the numbers do a little bit of work. And just because somebody tested positive doesn't mean they actually are positive.